Hello, my name is Claire Helmke. I'm a graduate student at Western Illinois University, and today I'll be presenting some of my thesis work on spatial distribution of extractable metals and sediment from iron foundry slag deposited at Carp Lake outside of Davenport, Iowa. The long-term goal of the Carp Lake property is to be used for education and outreach, but remediation of the site needs to happen first. This leads us to our objectives, which is to identify the spatial distribution of metal concentrations across the sediment to better inform remediation plans for this site and similar locations. If we can figure out where in the sediment metal concentrations are most focused, then we can target remediation efforts. You may be wondering where the metals in Carp Lake originated from. Metals are naturally produced within the Earth's crust, which are extracted from mines. The coal and iron deposits in the Midwest, along with the river and rail transportation systems, made the region a hub of iron and steel production during the Industrial Revolution. This increase in production requires new plants to be built, and new plants require new areas for dumping slag. Slag is a byproduct of the iron and steel production, essentially the leftover at the end of the smelting process, which is then dumped out while still molten and left to cool, creating porous and volcanic-looking rocks. Slag is composed of compounds relating to the ore it was produced from, meaning that slag can contain concentrations of metals including arsenic, beryllium, cadmium, copper, lead, and zinc. Initially identified as harmless, slag was dumped indiscriminately along shores, railroads, wetlands, and other undesirable wildernesses until the 1980s, when federal regulations began new disposal legislation. Atmospheric weathering of slag releases trace metals into the surrounding environment from where it was dumped, which can accumulate into the soil, the water column, sediment, and be absorbed within bacteria, vegetation, and animals. For every ton of iron or steel produced, a quarter ton of slag is also produced. In the 1970s, approximately 28 million tons of steel were produced in the Chicago area alone, resulting in about 7 million tons of slag being produced and dumped. I mentioned earlier that metals are naturally occurring in the environment, and many are necessary for life. It's why we take iron supplements and add it to our cereals. These are called essential metals. Non-essential metals like lead, arsenic, cadmium, and mercury pose a potential risk to human and environmental health, even at low levels. For example, the US EPA's maximum contamination level in drinking water for cadmium is 0.005 milligrams per liter. The chemistry of metals allows for easy transportation through aquatic systems as suspended sediment or storage as bottom sediment. Metals have indefinite persistence within the environment and can become bioavailable within the system, ready for absorption in plants and algae. This is why the EPA's priority pollutant list includes both essential and non-essential metals. Because slag can contain high concentrations of metals that are easily related to the environment, large deposits of slag have been managed and remediated by the US EPA as Superfund sites, such as the Sharon, Steel, and Midvale slag sites in Midvale, Utah, which contains 2 million tons of slag across 570 acres on the Jordan River. Another Superfund site is the Big Marsh site, which is a portion of the Lake Calumet cluster southeast of Chicago. It is up to 2 meters deep of slag across the 300-acre site. However, there's more than 52 square kilometers of slag deposits across northwestern Indiana and northeastern Illinois alone, and many of these sites are too small to receive federal funding and management from the EPA. Carp Lake is one of these sites. The 8-acre lake is on a 40-acre property. It is unknown when or how much slag was dumped to the site, but it was likely concluded by the 1980s. The property was purchased in 2002 by Nahant Marsh to be used as a site for education outreach. In 2017, the main slag deposit, which had been grown over with vegetation, was discovered, and an environmental assessment of the impact of the slag pile was conducted. Between the 2017 and 2019, an analysis of the slag pile, soil, sediment, water, and vegetation of Carp Lake revealed elevated concentrations of trace metals that could be directly linked to the slag pile. The metal concentrations of cadmium, copper, zinc, and nickel in the soils around the slag were higher than local uncontaminated soils, but below the regional screening levels. Mean concentrations of cadmium, lead, and copper in the water of Carp Lake exceeded the EPA's recommended metal criteria for aquatic life. And lead concentrations in the 5 surrounding monitoring wells also exceeded the statewide standard for a protected groundwater source for Iowa. Over the 3 years of the study, metal concentrations within the lake water varied, indicating a heterogeneous system. Continuous low exposure of a mixture of metals in the ecological system can cause chronic harm to the exposed plant and animal life. Due to the threat to human and wildlife health and safety, Nahant Marsh has been unable to use the Carp Lake property for its intended education outreach purposes. Carp Lake is part of the Mississippi watershed, the Mississippi Migratory Flyway, and habitat for threatened and endangered species like the Blanding's turtle. But as a small site, Nahant Marsh will need to manage remediation without federal assistance. The first step is to remove the slag pile. Then, because the lake's sediment is a storage for trace metals, removal of the sediment is an additional remediation step. This brings us back to the objectives of the study. Even for a small 8-acre lake, sediment removal is a massive undertaking. In the 2017 to 2019 survey, it is estimated that metals released in the slag pile could have collected in the sediments along the shore close to the slag pile, or in the deepest points of Carp Lake like a repository. So our objective was to identify the spatial distribution of metal concentrations across the lake sediment in relation to the point source. If remediation can be focused in a smaller area of the lake, that reduces the time, effort, cost, and impact of remediation efforts. This analysis will better inform Carp Lake's remediation plans, as well as be useful for managers of remediation projects of medium and small slag piles across the upper Mississippi River Basin. Carp Lake is only 400 meters from the banks of the Mississippi River, south of Davenport, Iowa, and Scott County. The lake was a former sand quarry created between 1944 and 1950, and is about 3.5 meters at its deepest. Interstate I-280 immediately borders the site to the northeast, the Canadian Pacific Rail Line to the northwest, undeveloped bottomland in the southeast, and the Mississippi River and several single-family residencies to the southwest. The property frequently floods from the Mississippi, so fish and other aquatic populations in Carp Lake are transient due to these floods. The primary slag deposit is on the northeast side of the lake. To accurately estimate the size of the slag pile, 4 soil bores were collected from around the estimated perimeter of the slag pile and the estimated highest point of the slag in October of 2020. These locations were decided on by the evidence provided from digital elevation models from LiDAR in the presence of large slag boulders around that part of the property. Looking at the soil horizons from the bores around the perimeter of the slag pile, you can tell the difference between the dumped foundry slag and the native sand based on just texture and color. From the soil bore placed at the top of the slag pile, the slag material you can see in the image on the right went down 2 meters. Coincidentally, the topography of the northeast shore of the lake is 2 meters higher than the surrounding area. With this data, we can confidently say that the area on the northeast shore of the Carp Lake was the location of the primary slag deposit. Using the available information from in situ observations, topographic maps, and the soil horizons, we were able to estimate the area of the slag pile to being 1,745 square meters. Using a 3D rendering program, SketchUp, we calculated the volume of the slag pile to 4,787 cubic meters. We collected 16 sediment samples across Carp Lake in May of 2021 with a Ponar dredge from a John boat. The 16 samples were randomly placed based on how shallow the lake got and how much the wind pushed the boat around. So our sampling location is the exact location samples were collected, which we use a Trimble GeoExplorer with post-processing to an accuracy of less than 100 centimeters. Each sample was drained of water before being emptied into the gray tub, which we washed between each sample. We homogenized the sediment sample, or sludge, and removed any vegetation and stored each sample in a labeled Whirlpack. That sludgy sediment samples we collected were then dried and ground into samples of 1 gram each. And we also included 2 triplicates for QA/QC. To convert a solid to a liquid so that we could accurately measure the extractable metal concentrations using a spectrometer, we followed EPA method 3050B for acid digestion. Each sample was exposed to 70% nitric acid, 30% hydrogen peroxide, and hydrochloric acid, and heated to effervescence. They were then filtered through a Wattman number 41 filter paper to remove any remaining sand particles, then diluted to 100 milliliters with type 2 lab water. Using a flame atomic absorption spectrometer and following EPA method 7000B, we were able to identify the extractable concentrations of cadmium, copper, lead, nickel, and zinc from the formerly solid sediment samples. To accurately assess the spread of the metal concentrations within the sediment, we need information on the X, Y, and Z plane. So we need to figure out how to collect depth from our sample locations. Using a Lowrance Elite 5 fish finder and sonar with a transducer mat attached to a kayak, we collected bathymetry data in November of 2021. In the same day, 2 of my lab mates surveyed the depths from each sample location from canoe using a survey rod. This was especially important because I ran ground trying to get sonar to that section of the lake west of the peninsula and couldn't continue mapping in that direction, but the canoe could. We utilized CMAP's EcoSound to convert the sonar files into bathymetry shape files using a kriging interpolation. Across Carp Lake, Singh had the highest concentrations of the tested extractable metal concentrations, followed by copper, nickel, lead, and cadmium. On average, the concentrations within the sediment were below the EPA's benchmark. However, almost half the copper samples were above the EPA's benchmark, and 2 of the nickel samples were above the benchmark. Cadmium and lead are both non-essential metals, so having lower concentrations of both of these metals is a good thing. The southernmost sample sites, samples 1 through 3, had the lowest metal concentrations, while sample 13 had some of the highest. Of all the metals, only nickel did not have elevated concentrations at the sample site west of the peninsula. We wanted to test if the extractable metal concentrations were either collecting in the deepest portions of the lake, like a repository, or concentrating around the slag pile. To analyze this, we ran 2 different students paired t-tests for small sample sizes. First, we separated the samples into 2 groups of 8. Those samples collected at a depth less than 1 meter and those collected at a depth greater than 1 meter. The second test separated the samples into 2 equal groups of 8 again, those less than 100 meters from the edge of the slag and those greater than 100 meters from the edge of the slag. Our null hypothesis was that there would not be any difference in metal concentrations based on either depth or distance. The t-test results looking at the depth of metal concentrations did not result in a t-value greater than the critical value, and so we failed to reject the null hypothesis, meaning that there is no difference in the metal concentrations based on depth. The t-test results looking at the concentration based on distance, the t-values were greater than the critical value and our p-values were less than 0.01, allowing us to reject the null hypothesis and find a statistically significant difference in metal concentrations based on the distance from the edge of the slag pile. So this leaves us with the information that metal concentrations are distributed heterogeneously throughout the lake sediment with respect to depth. This heterogeneity is also seen across the lake, but with higher concentrations closer to the slag pile, as was previously proposed. However, to accurately remediate the site, we cannot focus on only one part of the lake, but have to consider a plan that removes metal concentrations from all of the lake sediment. Potential remediation techniques include mechanical sediment removal, which would involve draining Carp Lake and using machinery to physically vacuum up or bulldoze the sediment to remove it from the lake bed. However, with the high water table and how sludgy that sediment is, mechanical removal would be almost impossible. The machinery would be stuck or restricted to an arm length of an excavator positioned on shore. We would still be left with the issue of disposal of the sediment after removal. Phytoremediation is another remediation technique that uses specific plants' abilities to accumulate metals within their biomass to remove it from the environment. After the plants have reached their peak growing and accumulation stages, the plants are removed and burned. Phytoremediation does take several years, but is much cheaper than mechanical removal and causes less damage to the habitat. A convenient aspect about phytoremediation to manage the metal concentrations at Carp Lake, the primary aquatic vegetation at Carp Lake is a species called coontail, and it has already been identified as a hyperaccumulator for iron, copper, lead, and cadmium. As you can see from the map for August 2020, coontail has almost completely covered the lake, except for those deepest areas. Coontail's ability to be used for remediation at Carp Lake is the next direction of our research. This will require figuring out the best timing for removal, as well as estimating the amount of time that will be needed to reduce the metal concentrations within the lake. And with that, I would like to take a moment to acknowledge and thank Nahant Marsh for working with us and their continuous help. I'd also like to thank my committee members and WIU's Institute for Environmental Studies, and my lab members and almost all who showed up at Carp Lake for the first blustery winter day for the benthic survey. And with that, I will take questions. Thank you.